In this lesson, we're going to look at how to deal with Lewis structures that end up being exceptions. So far, our goal in drawing the Lewis structures was to end up with the central atom having 8 valence electrons so that it followed the octet rule. So remember, the octet rule is the tendency for atoms to want to obtain that full outer shell of 8 valence electrons in order to be stable. So in NH3, nitrogen has 8 valence electrons in the Lewis structure. It's following the octet rule. What we're going to look at is how to deal with exceptions to the octet rule where the central atom doesn't want to have 8 valence electrons in order to be stable. The first type of exception is when the central atom wants to have less than 8. The other type of exception is when the central atom wants to have more than 8. So there's two elements when placed as the central atom. They want to have less than 8. So beryllium, if it's the central atom, it wants to have 4 valence electrons. So we can justify this using its electron dot structure. It has 2 unpaired electrons, therefore it needs to make 2 single bonds in order to become stable. So it wants 4 valence electrons when it's placed as the central atom. Boron, if it's the central atom, it wants to have 6 valence electrons. If we look at its electron dot structure, it has 3 unpaired electrons. Therefore, it needs to make 3 single covalent bonds in order to become stable. So it needs 6 valence electrons when it's placed as the central atom. So let's look at an example. If we have Bf3, my first step is to calculate the total valence electrons using the inventory. Remember, we're always checking that inventory before we move forward. We always want to make sure all the problems that we're doing in class are even. So 24 valence electrons is how many that I need to kind of incorporate into the Lewis structure. Boron is placed as the central atom. The 3 fluorines are placed around it. I'm connecting each fluorine to the central atom with a single covalent bond. That uses up 2, 4, 6 electrons, and I have 18 left over at this point. Now I'm going to go through and fill the outer shells. And just remember, as you're going through and filling the outer shells, you're subtracting. Keeping track of the inventory is key. And you can see when I fill that last fluorine, I reach the point where there's 0 electrons left over. Now when I check boron, it has 2, 4, 6 valence electrons. I have to recognize that boron is an exception that wants to have less than 8 valence electrons. It wants to have 6, that's how many it has, so it's done. You have to be careful not to add dots, or double bonds, or triple bonds to try to bring it up to having 8, because it doesn't want that, it wants to have 6. So this has 3 bonding pairs, 9 non-bonding pairs. 3 plus 9 gives me 12. 12 times 2 gives me 24. That's how many valence electrons I needed in the Lewis structure for Bf3. Now we need to look at these exceptions where that central atom is going to have more than 8. So when the central atom has 10 or 12 valence electrons, it's called an expanded octet. The elements that are in periods 3 through 7 can have an expanded octet where that central atom either ends up having 10 or 12 valence electrons. You will be forced to expand the octet by simply following the normal steps that we've used to draw a Lewis structure. So let's go through a couple examples. Let's look at PF5. Even before I do anything for this, I know that this is going to be an expanded octet because I can see that there's going to be 5 fluorines on phosphorus. If there was 6, same thing. So sometimes you can look at the formula and see that it's going to be an expanded octet. This is an example where I can look at the formula and see that. So I go through, I do my inventory, 40 valence electrons. I place phosphorus in the center. I put the 5 fluorines around it. I'm connecting each fluorine to the phosphorus with a single bond. That uses up 2, 4, 6, 8, 10 electrons. So now I have 30 left over at this point. Now I'm going through and I'm filling the outer shells of those outer elements. And as I'm doing that, remember the key thing is I'm subtracting, I'm keeping track of what I'm using up. And now I've reached the point where all of those fluorines have been filled and I ran out of valence electrons. So now when I check phosphorus, which is the central atom, there's 2, 4, 6, 8, 10 valence electrons. This is an expanded octet. I was forced to expand the octet by simply following all of the steps that I've been using in order to draw a Lewis structure. There's 5 bonding pairs, there's 15 non-bonding pairs. 15 plus 5 gives me 20, times 2 is 40. It matches how many I needed. All right, this next one, I can't tell that it's an expanded octet by just looking at the formula. I have to go through all of my steps in order to see that it's an expanded octet. So I go through and I see that there's 36 valence electrons. I'm placing xenon as my central atom, my 4 fluorines around it. I'm connecting them to the central atom. That uses up 8 valence electrons total. So now I have 28 left over at this point, and I'm being really careful as I'm going through and filling those outer shells of the outer elements that I'm subtracting. I'm keeping good track of what I'm using up, because what I'm going to see is I'm going to fill that last fluorine and I'm going to end up having 4 valence electrons left over. So I need to place any remaining electrons as non-bonding pairs on the central atom. I have 4 left over, so I have to place 2 non-bonding pairs on that central atom. The key thing is I need to clearly see that it's 2 separate non-bonding pairs. So I'm giving them their own space. I'm making sure it's very clear that there's 2 non-bonding pairs added onto that central atom. So now I've used up all of my valence electrons. When I go through and check xenon, there's 2, 4, 6, 8, 10, 12 valence electrons around it. Therefore, it's an expanded octet, and I stop. You will never use double or triple bonds with expanded octets. It's simply you're following the normal steps, and you're going to see that you're going to be forced to have either 10 or 12 valence electrons on that central atom. So there's 4 bonding pairs, there's 14 non-bonding pairs. 14 plus 4 gives me 18, times 2 gives me 36, so it has the correct number of valence electrons. All right, next one is IF3. So when I go through and I solve this, I have my inventory. Iodine is placed as the central atom. I have 3 fluorines that I need to place around it. I'm connecting them to the central atom, and I've used up 6 electrons, so now I have 22 left over at this point. I'm going through, I'm filling all of the outer shells. As I'm doing that, I'm subtracting, I'm keeping good track of what I'm using up. Now I've filled all of the outer shells, and now I have 4 valence electrons left over. I'm going to place them as 2 non-bonding pairs on that central atom. Remember, the key thing is I need to clearly see that there's 2 non-bonding pairs. So your placement of those 2 non-bonding pairs might be a little bit different than what I kind of just did, but I have to clearly see that there's 2 non-bonding pairs on that iodine. So now I've used up all of my electrons, and when I check 2, 4, 6, 8, 10, iodine has 10 valence electrons. It's an expanded octet. So once again, with the expanded octet stuff, if you know how to follow the normal rules and you're following them correctly, you either end up with 10 or 12 valence electrons on that central atom. So for this one, there's 3 bonding pairs, there's 11 non-bonding pairs. 11 plus 3 gives me 14, times 2 gives me 28. It matches how many valence electrons I need it to include in the Lewis structure.